is recording. Just being sure I see it counting up there. I would hate to be like done and then, oh, there's no video. Because then the audience at home would just be so disappointed. All right, so let's do it. Remember the way it works is ask me questions about anything on the guide or about the meaning of life or whatever. Eventually we'll get to the point where everybody's playing chicken. Like, you know, it's like, I don't know, I kind of want to go, but, and then enough people will leave and then we'll be done. So, I'll stay here as long as people want to keep asking me questions. Yes?
What's the focus of an eclipse? What does that mean?
Focus of a what? Oh, you mean an ellipse?
Yeah,
Focus of an ellipse, right? Yeah, focus of an ellipse, yes. So remember that Kepler's first law says that if you have a planet orbiting the sun, or a comet orbiting the sun, or a satellite orbiting the Earth, or whatever, the orbit is that special oval shape called an ellipse. And the sun, or Earth, or whatever the very massive body is the one focus of the ellipse. And what defines the curve as being an ellipse is the fact that for every point on the ellipse, if you add up the distances to the two foci, that's absolutely constant everywhere around the ellipse. So that's what, it's a different kind of focus from the focus of a lens. It's the same word but very different meanings. Yep. Any further questions about that? I always like to try to remember to follow up with. Everybody clear on that? Or somebody got something else you want to ask? Don't be shy. Yes?
I have a different question.
Sure, absolutely. Yeah.
I was just wondering, in regards to the scientific method, why it's important to make testable predictions.
Yeah, why it has to be testable predictions, because that's the only way we can tell if they're wrong, essentially. So, in other words, you know, kind of the ridiculous example that's sometimes thrown out there, the philosopher Bertrand Russell talked about Russell's teapot. So suppose we had a hypothesis that around the sun is orbiting a teapot. Who knows how it got there, but make the assertion there's a teapot orbiting the sun. Could we test it? Well, kind of hard, you know. In other words, there's no obvious way to discover whether or not that's false or not, because it's very hard to find a teapot orbiting the sun. Not likely. Even if there was, though, we wouldn't likely be able to find it. So we want our hypotheses to be testable, because we want to be able to do an experiment or make observations that could tell us if they're false. Remember that it's important that a scientific hypothesis be falsifiable, that you could do an experiment or conduct observations to show that it is false. If we make enough observations and we never show it's false, we're never sure that it's right. They become more and more sure that it could be correct the more experiments we run, observations we conduct that do not falsify it, that are consistent with it. But if it's not testable, it's not scientific, because we're not able to try to verify it. We're not able to try to show that it's wrong, essentially. And that's really all it comes down to. That's one of the things that makes it scientific, is that it's possible to test it and check whether or not it needs to be valid. Yes?
So what kind of quantitative questions will be on our test?
What kind of what?
Quantitative questions?
Quantitative questions. So, so anything is fair game from like the mastering astronomy, but I do tend to favor ones where you don't need to use a calculator on the exam. So the kinds of things where, you know, it would have to be like Compare the light gathering power of a 15-meter diameter telescope to a 3-meter diameter telescope, for example. You need a calculator to do that because you know that it goes like the square of the diameter of the lens or mirror, and so you'd say 15 meters is 5 times 3 meters, so 5 squared, 25 times more. That's the kind of thing I can even make multiple choice, and 25 would be one of the answers for something like that. You wouldn't need a calculator for that. So anything is fair game, but I tend to prefer things where the numbers are such that you shouldn't need to use a calculator, but you still need to understand quantity as far as that's concerned. Sometimes people think quantitative reasoning is about plugging numbers into calculators and getting results, but that's, you're not really, often you're not really thinking particularly when you do that. So I tend to prefer things where you're comparing things to one another, understanding how they vary in size or mass or so forth. Yes?
Can you explain what Occam's razor is?
Occam's razor, yes. So the question is, can I explain what Occam's razor is? Yeah. Has anybody ever heard of what's kind of jokingly referred to as the KISS principle? You know what that is? No, you guys haven't heard that before? The KISS principle is keep it simple, stupid. And that's kind of Occam's razor in a nutshell. I mean, I'm being a bit facetious there, but Occam's razor says if you have two hypotheses that are both equally good at explaining the data, explaining the scientific data, we generally find that you should prefer the simpler one. So Occam's principle is the idea that scientific explanations should be as simple as possible, but not any simpler, right? In other words, not so simple that it doesn't explain the observations. But while I can't give any profound reason, I don't think anybody can, as why it seems to work. Why do simpler explanations tend to end up being correct? Nevertheless, nature seems to be so far pretty generous that way. And so it's nice if you can get away with the simplest possible explanation. Certainly that would be what you would like to be able to do, and nature seems to be okay with that. Occam's razor has generally been a pretty good guide. And so, for example, one of the reasons to prefer the Copernican model of the solar system, where the sun is at the center and the planets are going around it, as opposed to the old Ptolemaic system where everything is going around the Earth, which in order for us to explain the motions of the planets with any amount of precision required planets to be moving around larger circles going around the Earth, and then also moving on smaller circles that were moving around those larger circles. It was a very complicated system, and the final model that we have with planets going around the sun on elliptic orbits and so forth dispenses with all that. It's simpler than the wheels within wheels kind of model that the ancient Greeks had. And that's an example of Occam's principle, Occam's razor in action, kind of shaving away all of the unnecessary details. Any further questions about that? Okay, you have a question.
Yeah, can we review Wien's law and the Stefan-Boltzmann law?
Yeah, so Wien's law, yeah, I know. Here in America, we tend to say, woo, woo, woo when we see a W, but it is Wien's law. Wien, the capital of ASTR. But it's named after the physicist Wien. So that would be light matter. So let me find the magic slides for that. So we'll start with Wien's law, even though I got them in the other order of the slides here. So Wien's law is the one that is the reason why, remember when I had the light bulb and I cranked up the temperature of the filament by dialing up the voltage? It did two things. One is it got brighter, the other is it changed colors. It started out when it was glowing kind of this dull orange color, and as I heated it, it got kind of yellow, and then yellowish white, and then white, and I couldn't get it any hotter. It would have broken the filament, but eventually it would have turned bluish white. And it's related to the fact that if you look at the black body spectrum, if you look at the thermal spectrum from an object, the peak wavelength, which is what Wien's law refers to, the wavelength where the spectral curve for the black body has its maximum value. You can kind of think of it as the wavelength at which the object is emitting most strongly. The peak wavelength is given by Wien's law. In words, it says that the hotter the body is, the shorter is the peak wavelength. And so we can see that here. So here's a 310 Kelvin human, where the peak wavelength is around 10,000 nanometers. Here's a 3,000 Kelvin star. The peak wavelength is closer to 1,000 nanometers. The sun, 5,800 Kelvin, it's more like 500 nanometers. The 15,000 Kelvin star peaks at even shorter wavelengths than the ultraviolet. That's, in words, what's going on. Hotter means bluer, is another way to put it. The peak wavelength becomes shorter as the temperature gets higher. And more specifically, the formula is given by this right here. The temperature, so you can either know the peak wavelength and use that to figure out the temperature, and if that's the direction you're going, the temperature is this number, 2.9 times 10 to the 6 millimeter Kelvin, divided by the peak wavelength. So that would be if you measured the wavelength of the peak and wanted to figure out the temperature, or you could turn it around, you could solve that for the peak wavelength. So if you do that, then the peak wavelength is that same number, 2.9 times 10 to the 6 nanometer Kelvin, divided by the temperature in Kelvin. The temperature has to be in Kelvin. So this is saying as T goes up, here in the denominator, lambda goes down. That's the mathematical statement. It's the one that lets you plug in the numbers if you need to do that, and say what the peak wavelength or the temperature actually is if you know one of the two of them. Yes?
So what all would you need to solve a problem like that?
So if I said something like, what is the peak wavelength for the sun? You could plug it in. You could say, okay, so for the sun, so I have to tell you one or the other. I either have to tell you the temperature or the peak wavelength. I'm not going to be like, okay, go measure with a spectrometer the sun spectrum, and from your observations, deduce its peak wavelength. I could tell you that, but not amazing. So the sun, the temperature of the sun, 5,800 Kelvin. And so you put it in. Lambda peak is 2.9 times 10 to the 6 nanometer Kelvin divided by 5,800 Kelvin. Notice that the temperature units of Kelvin cancel out, leaving you with nanometers, which is what you want because the wavelength is a distance, and nanometers are a measure of distance. And 2.9 million over 5,800 is, in fact, 500 nanometers, is what you would get if you put that in your calculator, or notice that 29 over 58 is a half, and then you could deduce it. You actually could do that printable without a calculator. I wouldn't expect you to necessarily do that, but it wouldn't be too hard to do so. That's what you would do. So the peak wavelength for the sun's 500 nanometers, just like the plot essentially indicates. The peak is at 500 nanometers for the sun, for example. Yes?
So you said the object's hotter, the peak wavelength.
The hotter the object is, the shorter is the peak wavelength. So notice that for a 3,000 Kelvin star, the peak wavelength is right here, right? In other words, the wavelength on the x-axis corresponding to the peak of the curve, where it's highest on the y-axis there. That's what we mean by the peak wavelength. The wavelength where the object is emitting the most radiation, if you will, because that's what this is a plot of. It's brightness versus wavelength, essentially. If I go to the sun, 5,800 Kelvin, its peak wavelength is over here. So 3,000 Kelvin over here, 5,800 Kelvin over here, towards shorter wavelengths.
And so intensity has no effect on
This is just telling you the wavelength at which it's brightest. What's also true is that out of every square meter of the surface, more energy is coming out when you raise the temperature. So notice that the curve for 5800 Kelvin is everywhere taller than the curve for 3000 Kelvin. So every square meter gets brighter, and the peak, where it's emitting most strongly, goes to shorter wavelengths. So for the 3000 Kelvin star, the peak, where is that? Is this in the visible? This peak like right here? No, where is it? It's in the infrared. It's at longer wavelengths than visible. So that star's peak is in the infrared, but it is emitting visible light. And notice that it's emitting more on the red, orange, yellow side than it is over here, lower down on the green, blue, violet side. So a star at that temperature looks reddish to our eyes as a result, because we're seeing more red light from it than we are blue light, essentially. Red, orange, yellow than green, blue, violet. The sun has a more even mix, which is why it looks pretty white to our eyes. And then the 15,000 Kelvin star has more, its peak is in the ultraviolet, but it's got more energy coming out on the green, blue, violet side of the visible spectrum than it does on the red, orange, yellow. So a star that hot looks bluish to our eyes because it's emitting more on the blue side of the spectrum than it is on the red side of the spectrum. So Wien's law, the shift of the peak, is correlated with that change in color as the temperature increases. Yes?
Just a curiosity question. Can we actually, or are there any stars that we can see that are like actually violet purple colored?
No, none of them ever turn purple to our eyes. And it's because what we see is a combination of what the star is emitting and what our eye's sensitivity is, and so forth. So notice that, yeah, this star is actually brighter at purple wavelengths than it is at blue wavelengths, but our eyes have a blue receptor, and a red receptor, and a green receptor, and it works out that we are more sensitive as a result of that to blue light than we are to purple light. And so as a result, it still looks blue to us. It'll look bluish white, actually. It never looks purely like beautiful blue or anything like that. It would look bluish white at most to the eye, even at very high temperatures. Yes?
I'm kind of confused on how you were wording some of this stuff a minute ago, because you were saying, like, the hotter the star, like the shorter the peak wavelength.
Mm-hmm.
But like when I look at that graph, I automatically think the red one's hotter because it like the peak is shorter. But you mean like
No, so careful, because you have to distinguish between the x-axis and the y-axis.
yeah.
So in other words, when I say the wavelength is shorter, that has nothing to do with the height of the graph.
Yeah. So
What I'm saying is that if I go down, here's the peak right here. Here's what, so the x value, wavelength is on the x-axis. The x value right there is the peak wavelength. So here, the peak is at about 10 to the 3, 1,000 nanometers. Whereas for the sun, the peak is over here, 500 nanometers. So when I say shorter wavelengths, I mean further to the left on the x-axis here. So where the peak of the mountain is moving to the left along the x direction is what that means.
Thanks.
Yes?
Can we go over the light diffraction?
Not yet, because we just did Wien's law, but you also asked about Stefan Boltzmann. But we can't, so hold that thought. Yes. No, wait. I want to do Stefan Boltzmann first. Hang on. Okay. Any more questions about Wien's law? Okay, time for Stefan Boltzmann. So this is Stefan Boltzmann. Stefan Boltzmann law describes the fact that hotter is brighter. Wien's law describes the fact that hotter is bluer. Stefan Boltzmann law is the one that says hotter is brighter. Remember when I cranked up the light bulb filament, not only did the color change, it also got brighter and brighter and brighter. It got kind of annoyingly bright. That's described by the Stefan Boltzmann law, which says the total amount of energy emitted out of each square meter of the surface every second, which we call the flux, is given by this constant of nature, the Stefan Boltzmann constant, multiplied by the temperature to the fourth power. And I don't care about you plugging in a temperature and multiplying and taking it to the fourth power and multiplying it out and getting a number for the flux. That's plugging into a calculator. That's not particularly thinking. That's kind of mindless. What I do want you to understand is what happens when the temperature changes because of the fact that it goes like the temperature to the fourth power. So this is that business where whatever I do to the temperature, I have to take it to the fourth power to figure out what I did to the flux. So for example, if I had two stars, and let's say one of them is at 8,000 Kelvin. So here's star one, its temperature is 8,000 Kelvin. Here's star two, its temperature is 16,000 Kelvin. And the question is, how does the flux from star two compare to the flux from star one? First of all, which star has a higher flux? Not a trick question. T1 or T2, which flux is bigger?
T2.
T2, the hotter star. Hotter is brighter. Now, how many times hotter is star 2 than star 1? Twice as hot, right? Because 16,000 is twice 8,000. So to figure out how big the flux is from star 2 compared to star 1, I take the fact that it's twice as hot, I raise that to the fourth power, so the flux from star 2 is 16 times bigger than the flux from star 1. That's the kind of quantitative problem I want you to do using Stefan Boltzmann law. Figure out how many times hotter one star is than the other one, raise that to the fourth power, that's how much bigger the flux from that star is. The hotter star's flux is however many times hotter it is than the cooler star, to the fourth power, that's how many times bigger its flux is. So, twice as hot to the fourth power is 16 times the flux. If you want to get fancy, what we'd be saying is that flux 2 divided by flux 1 is temperature 2 divided by temperature 1 to the fourth power. So that would be 16,000 Kelvin over 8,000 Kelvin to the fourth power, but 16,000 over 8,000 is 2 to the fourth power. So you can do all that, or you can just say it's twice as hot, 2 to the fourth power 16. Whichever floats your boat. I tend to do it that way because it's quicker, as long as you can think of it like that. That works just great, gives you the same thing. Yes?
So are you saying the flux is 16?
The flux is 16 times bigger. The flux from star 2 is 16 times bigger than the flux from star 1.
So we just ignore the constant then?
Yeah, you don't need it. You don't need the constant, because notice that if I did take the ratio, that cancels out. That's the great thing. To answer a question like this, it doesn't matter what the constant is, because F2 divided by F1 is sigma T2 to the fourth power, because that's the flux from star 2, divided by sigma T1 to the fourth power, because that's the flux from star 1, but the sigma in the numerator cancels the sigma in the denominator, and T2 to the fourth over T1 to the fourth, the rules of algebra say that's just T2 over T1 all to the fourth power. So that's the full derivation of the fact that sigma doesn't matter. The value of, for answering this question, sigma doesn't matter. Now if I had a different question, if I said, what is the actual flux from star T2? Then I would have to take that number sigma and multiply it by 16,000 to the fourth power. But that's not what I was asking. I was asking how many times bigger is the flux from the second star compared to the first star. Yes?
Are we gonna have to memorize the constant?
Oh, no.
Okay.
No. I will give you a list of formulas and constants. You don't have to memorize those. I mean, I've memorized a lot of them just by accident, seeing them all the time. This one's not too hard because it's 5, 6, 7, 8, 5.67 times 10 to the minus 8, so that was pretty easy, but no, you don't have the answer. Okay, Any more questions about Stefan Boltzmann law? Yes?
Can you explain the letters at the end there?
The letter, you mean this stuff? The
Yeah.
blah, blah, blah. This is the units. So watts per square meter per Kelvin to the fourth power. Those are the units of the constant because you have to get the final units right. So the way that works is, again, if I wanted you to actually find a flux, notice that you'd be going flux equals, you'd have in terms of units, watts per square meter per Kelvin to the fourth power multiplied by a temperature to the fourth power, but temperature's in Kelvin, so Kelvin to the fourth would cancel this per Kelvin to the fourth, leaving final units of watts per square meter. And m to the minus 2 means meters to the power of minus 2, which is the same thing as watts per square meter, which is what units of flux are. Energy per second per square meter is watts per square meter. So those are there to get the units right, is what it comes down to. But again, I'm actually not going to ask you to plug in and tell me a flux, what the actual flux is. I'm more interested in your understanding what happens when you change the temperature. What does that do to the flux? Understanding that it goes like the fourth power of the temperature, so that a small change in the temperature produces a much bigger change in the flux. Doubling the temperature doesn't double the flux, it makes it 16 times bigger, and so forth. Any more Stefan Boltzmann questions? All right, I saw your hand, but I had a number of, so we'll get to you. So you had you had another question, yes? So
The light absorption calculation, how, because I recall in class you said it was like 4 times most.
light absorption calculation. So what are you referring to in particular?
So like when we were given the diameters of the lenses and we were told.
So you're talking about like if I'm comparing two telescopes to one another. Yeah, there I'm not talking about light absorption. I'm talking about light gathering power of the telescope. How much light the lens or the mirror is able to gather and focus to form the image. And there the idea is that the light gathering power depends on the area of the objective, the lens or mirror. The main lens or mirror of the telescope, its area is what is collecting the light from a star or other astronomical object or even a terrestrial object. And generally lenses or mirrors are circular in outline. And if I have a circle of diameter d, the area of that is pi d squared divided by 4. It's pi r squared, but the radius is half the diameter, so it's pi times the diameter squared over 4. So again, the important thing, if I'm asking you to compare two telescopes, is that it goes like the diameter squared. Because if I take a ratio of the area of one telescope to the area of the other telescope's lens or mirror, the pi over 4 is going to cancel out in the ratio. So that all that matters to us is that the diameter squared is what is involved. So it would be similar to the Stefan Boltzmann problem, except that instead of the fourth power, it's the second power. So for example, if we had telescope 1, the diameter of that telescope is 3 meters, and telescope 2, let's say its diameter is 9 meters. And the question is, how much more light gathering power does the bigger telescope have compared to the smaller telescope? That'll be how many times brighter a star image from the second telescope is for the same star viewed through the first telescope. What do? Same kind of thing. How many times bigger is the telescope 2's diameter than the telescope 1? How many times bigger is it? 3 times bigger. So it's 3 times bigger. And what power am I going to raise that to figure out how many times brighter its image is? 2. So I raise 3 to the 2nd power, which is 9, right? So in other words, making another telescope 3 times as big doesn't give it 3 times as much light gathering power. It gives it 3 squared times as much light gathering power. So 9 times as much light gathering power. I very much like asking questions like that as multiple choice questions because it's a quick way to test your quantitative reasoning. And so I do tend to ask those kinds of questions as multiple choice. Any more questions about that? Hey, Joe, I think you had a question you were going to ask me before. Yes?
My question is about chapter 3.
Chapter 3.
I don't know what exactly scientific hypothesis models part series of laws.
Yeah, so
We have to
right, like know what they are. Yeah. So let me. Your book talks about these ideas. I do have a slide that I did from. Actually, I don't think I have this particular slide on this year's presentation because I changed things up a bit, but I can add this to it. Whoops. So in scientific terms, in everyday English, a model will be often like a small version of something, like a model automobile or something like that, a model car. In science, a model is a carefully devised mental conception of how something works. And examples would be if somebody makes a tinker toy model of a molecule, where you've got like sticks and tinker toy, like discs or spheres or whatever, and you connect them together to make a representation of the arrangement of the atoms in a molecule. Does it tell you everything there is to know about the molecule? No, it's not telling you anything about the shapes of the quantum mechanical orbitals of the electrons or anything like that. But nevertheless, as a simplified conception of the molecule structure, it's useful to help us in thinking about it. Another example of a model in science is we make mathematical models of the interior of the sun. We can't go inside the sun, but we can solve the equations of the laws of physics that describe it with a computer, and we call the resulting descriptions tables of changes in density and temperature and so forth as a function of distance from the center of the sun. We call that a mathematical model of the sun. And then let's see, what were the other ones in there?
hypothesis models and facts.
Yeah, so remember, we did go about facts and theories in science. Remember that fact in theory in everyday English, it's often used as a fact is something you know for sure, and a theory is just a guess. But that's not what it means in science. In science, facts are the things we observe to be true about the natural world. Theories are explanations of facts. They're not guesses, they are explanations of facts in science. And then hypothesis, that's an educated guess about how something works, and it has to be consistent with what we already know. It's what you start with in the scientific method. An educated guess about how something works, and then you do experiments or make observations in order to test it, and you have to keep refining your hypothesis if the experiments are telling you that it doesn't completely work. So that's essentially the ideas there. And there was a hand back. There was a hand. Okay, all right, yes.
Yeah, it was kind of similar to this. It's like, what is a law?
So a law, yeah, so what's a scientific law? There's no hard and fast rule about when something becomes a law, but a law is essentially a very well-tested theory. theories in general typically are very well tested explanations before we're even willing to call them theories. There's exceptions to that, but usually before we even call something a scientific theory, it generally has undergone a lot of tests and passed them successfully. So an example would be the theory of evolution by natural selection, Newton's theory of gravity, Einstein's theory of general relativity. A law is a theory that has been so well tested, we're so confident in it, that we call it a law. But there are things which we're very confident in that we don't call laws even though we could. So there's no hard and fast rule there. So what we call, like Newton's law of gravity is the equation F equals g m1 m2 over distance squared. Look like you have a question. Yes?
So even though laws tend to be very well tested, could it be possible that at some point in time somebody like tests it and they come up with something
That's a great question, yeah. So even though a law is very well tested, is it always possible that eventually it will be overturned? And the answer is absolutely yes. We never in science have a situation where we are absolutely certain that something is right such that we are not open to revising our understanding if observations demand us to do so. Now, if something is really, really well tested, generally what will happen if we revise it is we discover that there are typically extreme situations where the law breaks down and has to be replaced by something more precise. So for example, Newton's law of gravity that says the force law between particles at a certain distance with certain masses. That was overturned by Einstein's theory of general relativity. General relativity is a theory of gravity that superseded Newton's theory of gravity. It's more precise, applicable under a wider range of conditions than Newton's law of gravity is. It's a very different picture of how gravity works according to general relativity, and we'll talk about this when we talk about black holes later. According to Einstein's general relativity, gravity is a curvature of space-time caused by mass and energy. And the reason why things respond to gravity is they are moving through curved space-time, which causes their trajectories to appear curved to us. And so it replaced Newton's law of gravity. But that doesn't mean we just completely threw Newton's law of gravity out the window, because Newton's law of gravity is much simpler than Einstein's, and often it works just great. So for example, when we pilot interplanetary spacecraft to other planets, we don't use general relativity because it's much more complicated than Newton's laws are. Newton's laws are good enough to pilot spacecraft through the solar system because the gravitational fields aren't very strong. But when gravitational fields are very strong, we start to see that Einstein's theory of relativity makes different predictions noticeably than Newton's laws do, Newton's law of gravity does. And so we have to use Einstein's general relativity when we're describing black holes, for example. So yeah, a law can be replaced, but generally it's so well tested that what happens is that we find that it's not always applicable, that there are things to which it doesn't apply and something more general is needed to replace it.
How about that?
How about what?
Fact.
A fact. So facts are different because, so